Have the next talk by Dario Passos. He will be talking about a low order model of the dynamo, solar dynamo, hopefully.
Actually, I apologize. The title of the talk changed a little bit, so it will be low order dynamo model and possible applications for that thing. So I'm working in Lisbon. I'm doing my PhD there under the supervision of Professor Lidio Lopez. And the idea, what I'm trying to present here is more an idea, a concept, maybe. So the idea is we have this time series of sunspots. So I'm working on solar physics, by the way. We have sunspots. This is the monthly average number of sunspots. And we have that, it's the longest time series we have to characterize magnetic activity on the sun. So people apply a lot of statistics to this and try to take out some information. And we thought, okay, maybe we can do the same thing and try to extract information about the dynamo. Okay, so the idea is, first of all, to build a proxy for the magnetic field. And we do that taking into account the picture of rising flux tubes, and sunspots are a signature of the toroidal field. Basically, we assume that the field is proportional to the square root of the sunspot, or the inverse. The sunspot is proportional to the magnetic energy, B squared. So basically, if we do this, and we apply that to that time series, we get, in gray here, we have the time series. What we do is that every magnetic cycle is composed by two sunspot cycles. So in order to take the polarity inversion, we change the sign of the data. So we make negative, positive, one magnetic cycle, negative, positive, another magnetic cycle, etc. And it's what we see here. So what we have here represented is the magnetic cycles since 1750 till 2000, more or less. That's on gray. The black line, it's a smoothing filter that we put, an FFT filter that cuts lower frequencies. And this helps in two ways. First, since we're interested in calculating derivatives in a bit, it helps us to get smooth curves for the calculus of the numerical derivatives. And second, since we cut lower frequencies, we are binding ourselves to specific time frame phenomena of the dynamo. So we're not looking into a small scale dynamo phenomena that might appear near surface. For example, we are interested in the long scale. Okay? So the filter that we apply here is like 18 months. So we don't have any signal from anything below 18 months. So with what we do afterwards is we build the phase space of this thing, of this proxy, and we have here dB dt, and we have here B. So we have this phase space. And basically, the way to read this phase space would be like the cycle begins here, for example, and then it grows until maximum amplitude of B, and then it decays, and then the other cycle. And every time it gives one complete turn in the phase space, you have a magnetic cycle. Okay, now we have this picture, and now we need to connect this somehow to theory. So again, we pick up axisymmetric mean field dynamo theory, and we couple it with this dynamical system analysis that people do in other fields. And just for the wrap-up, basically what we do, we use the axisymmetric dynamo model equations. These ones were pictured in Charbonneau's review, in the Living Review in Solar Physics. And this work was also already started by Pablo Minini in 2001, and I think Pontieri, an Italian guy, in 2003 also have a paper, very, very That looks very like Pablo's meaning work and Daniel Gomez. So basically the next thing is to, okay, we do not want to handle all these complicated things. So we want to reduce the order in order to obtain the dynamical model. So how do you do this reduction? This can be done several ways. It can be done by dimensional analysis, it can be done by variable separation. The most basic thing is to consider a truncation of the dynamo. So instead of considering del, the derivatives, we are considering just a characteristic scale, 1 over L0. We do that on this equation. We couple the terms, and we get something like very quickly, you get dB dt equals C1b plus C2a plus blah blah blah, and dA dt equals C3a plus C4b, etc. And
save it.
Okay. Now I'm staring. And basically what this does, these coefficients here contain all the structure of the sun. So meridional circulation, rotation, everything that's here outside these coefficients, the p's, are going to be compacted somehow here. Then what we do, we derivate this equation, we substitute this in there, and basically we end up with this expression over here. And this expression is what we call, everyone calls the Van der Pol-Duffing oscillator. And this equation, the stable solutions for this equation are in the phase space, as depicted here, are, I think I killed the laser. Yeah.
So can you show the previous slide where from the nonlinearities come?
Yeah, the linear, okay. The nonlinearity comes from this term here, which is the transport it has to do with buoyancy transport. Okay. So what I know from this term is that they're assuming that the buoyancy transport is proportional to magnetic buoyancy. So you have a b squared there, and you multiply it by the other term, you have b cubic, and that is going to create the nonlinearity in the system. So basically what we have here is this solution, the stable solution, it's an attractor in the phase space. So if I put a dot here, and things starts evolving on the phase space, sometime afterwards you would go to this solution. If I put a dot here, it will go sometime around, and it will go to this solution. Okay? Depending on coefficients omega, mu, chi, and lambda. So depending on those coefficients, you might have stable solutions, growing solutions, or decaying solutions. So this is the grouped things, omega, mu, chi, and lambda. Now the thing is, okay, now we have trajectories, stable trajectories, and we have that phase space that we built in the beginning. So the idea is, can we couple these two? So what do we do next? Basically what we do is we divide every magnetic cycle and we fit that expression. So on top left you have magnetic cycle number 7, and then we fit the thing, and we got mu1, chi1, lambda1, coefficients corresponding to that cycle. And the assumption here is that as a first approximation, we consider that each magnetic cycle can be corresponds to an equilibrium solution. Okay, we know that's not truth, but in first approximation, we can go with that, I hope. And basically what we do is that. Basically what we're saying is, even if the magnetic field changes, we are considering that the background structure, the radial velocity, the rotation, they are changing too, but from cycle to cycle. This is what we are doing. So, so here we have the fit. Oh, sorry. Maybe people are not seeing. What we have here in gray, it's the smooth version of the previous, the experimental data, and in black, imposed, we have the fits from the data. So we see that more or less it follows the same behavior. Okay, it has parts where it's a lot different, and we know why. Because when we have irregular cycles that don't look like a van der Pol, the fitting algorithm just goes berserk and cannot fit. So that's one thing that we are actually working right now. So, okay, we now accept, if we accept that the variation in those coefficients from cycle to cycle has something to do with the background, then we are saying that the background is changing from cycle to cycle. Okay, so if we go back into this expression here, for example, in this kind of oscillator, each parameter controls something. Omega corresponds to the frequency of the oscillator. Mu controls the asymmetry in the growth and decay of the curve. Mu together with chi controls the amplitude, and lambda, it's a weird little bastard that messes up everything by a little amount. Okay, but it mainly introduces some irregularity with omega in the frequency. So if we go here again, and now what we're going to do is we look to the simplest term we have, which is mu. That looks like this, and we see that it depends in what physical parameters. Meridian velocity, the Vp, eta, and L0, the characteristic length scale. So if you plot some numbers here, you see that, for example, this is like for the sun surface. It's like 20. L0 will be like 10 to the power 7. Eta is the turbulence diffusivity, which is 10 to the power 7 meters squared per second, more or less. And this is 10 to the power 14. Okay, you'll see that this term dominates. So, first approximation from cycle 1 to cycle 2, mu, change it. That means that probably the real velocity changes from cycle 1 to cycle 2. So we can derive a variation profile for the radial velocity through time. So that's what we have here. In the vertical axis, on the top graph, we have variation of Vp in percentage relative to cycle 1. Okay? And that's the black curve. The red curve, it's only considering half of the variation. Okay? Just to see if the model is giving something that could look like a reality, one thing that we can physically measure is the period of the cycles. And if we can experimentally have, without the fitting method giving us values, we can measure, like we know that the cycle in the phase space takes 2 pi over the time, and that's what we have here in red. And in black we have omega from the fitting method. So the overall behavior is the same, and it's overestimated. Why? Because the fit was done not considering lambda. Okay? Because the lambda value is usually very, very small, step to the power 4, step to the power 5. And you can do the fit without it. The results is not very different. But as I came to understand not too much time ago, it matters a little bit. And that's, I think that's why we see that degeneracy over there. And of course, the fitting method is not perfect. So basically, we have that profile of meridional velocity variations through time. So we can claim that. But we could claim that it could be a donut or whatever. Can we have any more physical input if that might be true? So we got ourselves a copy of Piali's code, and we thought, okay, if this works, or if this is more or less plausible, then if you plug in that meridional velocity profile into the code, you should get a response more or less like the ones you see on the sunspot cycle, right? So, without questions the physics, without behind the code, what we did was we simulated 2 sunspot cycles, then we changed the meridional velocity by the same percentage that we calculated, then we calculated a magnetic cycle, changed meridional velocity, calculated magnetic cycle, changed meridional velocity, and here we go. And we looked into the number of eruptions the code gives us, and we assumed that is our sunspot count. So on the top panel we have the annual observational sunspot number, and we have 3 possible reconstructions using those 2 profiles. Sunspot reconstruction 1 is changing meridional velocity at sunspot minima prior to the 2 next sunspot cycles with the full variation curve. What we see there is that, for example, this part over here that corresponds to magnetic cycle number 3 almost gets suppressed. We get like a Maunder minimum there. And why? Because we overestimated, of course, the variation in the meridional velocity. So we killed the dynamo, basically. And why is that? Because sunspot cycle number 8 and 9, which corresponds to magnetic cycle 3, it's very odd. It doesn't look anything like a Van der Pol oscillator. It looks like an egg. So the fitting algorithm just gave us a value that is most probably not true. And sunspot reconstruction 2 is changing the meridional velocity in the maximum prior to the next 2 cycles. So we actually simulate 2.5 cycles, 2.5 sunspot cycles. And we get that response. And this one here is using half of the variations that we found. Okay, so it looks more or less the same, but we like numbers. So we calculated the correlation for maxima, which is the red curve over there, and we calculated the correlation between experimental in each one of those for minima, which is the green curve, and we got this correlation coefficients. So for the minima, it's not very good, and I know now why. Because Surrey code, you get overposition between when one cycle begins, the other one still has a big tail. And I've been talking to Piali, and I really know how to get rid of that now. So these results need to be reevaluated. So basically, just to wrap up, the idea is you have long time series of sunspots. You might want to get ideas to take out information about the dynamo evolution, if we can say so. And this method with the phase space, fit, and etc., we think that might help. This what I showed here is a test case. So the conclusions. Okay, the method that I said, we can use the evolution of certain background structures, hopefully, within the theoretical framework of the work, meridional circulation variations can account at least for part of the variability that we observe. So in the future, what we would like to improve, and that's why I'm here in part of it, is to improve the theoretical model behind the method. So those coefficients can depend on different parameters. You get the same expression, but the physical dependence on the spatial coefficients can be a little bit different if you change different models. We'd like to introduce an adaptive fitting method. Actually, like a month ago in a conference, we met a high-energy physicist that is working with people that are studying brains, and they have published this new adaptive fitting method for dynamical systems that study the propagation of electric impulse in the brain. So we might use that, which is funny. And we would like to use the method, hopefully, to impose new constraints to dynamo theory, if that's even possible, and study long-term trends in the dynamo action or the background structures. And that is what we would like to.
Questions, please.
Is it known how these kind of equations respond to additive or multiplicative noise?
I think that Paolo Minetti did something like that in his paper, and what I've done is I have studied but you were saying about B, adding noise in B or any other, or any of the coefficients?
In the coefficients.
In the coefficients.
Right.
I've tried to add a stochastic component to the alpha effect.
Okay.
To the alpha, and you have modulation. Actually.
Does that mean your two trajectories go away rapidly, or
the system didn't become unstable.
okay?
So you didn't have growth, exponential growth or decay. It's for at least for the range of values I tried, it was solid. It oscillated the amplitude of each cycle, but it didn't die.
So you sound with that.
Yeah. One thing that killed the thing for some time was what happened if we stall meridian velocity for some time, and that died. I think I have the graph here somewhere. I knew someone would have asked me that. So that's here.
Yeah.
So basically, up there, what we do is we add a random stochastic fluctuation to the alpha effect, and you have some variability. You don't have what we would like to simulate a Maunder minimum, and a Maunder minimum in the phase space would correspond to a collapse to the phase space. So the V would go to 0, depending on which V we're talking. If it is on the base of the convection zone, it doesn't need to go all the way to 0. It just needs to go be below the threshold needed to buoyancy to come up. If it is at the surface, then it is 0. And this is a difficulty that we are having with the model, is the interpretation of the physical parameters. Since we lowered the order, things get a little bit messy. That's what we're doing right now. So this is by increasing chi, which corresponds to lowering the meridian velocity. And you have something evolving, and then all of a sudden it goes to 0, and then the thing comes back and it regains. So that's what we have. Yes.
A couple of questions actually. The nonlinearity, you said in response to Anval that you've got buoyancy there, so that's part of the nonlinearity. There's a lambda b squared, yes?
Yes.
Did you also have alpha quenching? Or?
No.
No alpha quenching?
No alpha quenching.
Is there any particular reason for not?
No, just we went for the simplest thing, which is the linear alpha. Although,
so you're marginally excited all the time.
so, yeah.
Marginally excited.
Yes. But actually, Paul Chabriot, he read our work some time ago, and he thinks that this can be used for impose some restrictions on the quenching methods the alpha factor. And actually I'm going to work with him in a couple of weeks on that.
There's another slight question too. You just replaced the derivatives by 1 over r, but I mean, I think as we had discussed before, in a sense it's I over r, isn't it, in each derivative, because you get a dynamo wave.
It's sorry, what?
I over R, he wants dynamo waves.
Because, I mean, these things are sort of essentially dynamo waves, yes?
Yeah, you can say that. I can actually don't know how to ask you a question, to answer your question. I have seen this method of just substituting this in principles is characterizing just one particular scale.
Yeah.
So instead of a solution curve, you just look at one point. So yeah, one other thing that could be done is to, in the beginning you start with saying that gamma that appears, the bisetter, is linear. You don't assume anything. Yeah. And then you do a variable separation. You say that your field is a spatial and a spatial part and then a temporal part. Then gradients and rotation and curls apply to the spatial, and the derivatives, the time derivatives just apply to the other part. And then you get to a set of equations separable. And then you propose an ansatz. And in there, first you do the cleaner, and then you propose the ansatz, and then you say, okay, now we have this term here, we can propose that is cubic, and you introduce that, and you get the same thing. Okay, you get one or more two parameters, that depends on the field, but the shape of the thing is the same thing.
Please.
How strong does your results depend on overlapping of cycles? Overlapping. Because cycles high, the overlap is sufficiently strong.
Yes, the minimum, the correlation we got for the minimum here. So if you squint like this, they look alike, at least in this part over here. But this part over here is where we have the larger error. So you don't need to squint; you really need to close your eyes. And yeah, since the code that I use also has a big overlap in the cycles. Basically, the butterfly diagrams that you get from that version of Surya that I worked with, you get something like this. This is the equator, and it has a tail here, and then yeah, it has a big overlapping zone. So I don't know if that is any real, or do you think that's real? Because usually we only see sunspot number, which is an integrated number, and we don't see if the spots that are contributing for here, the polarity of those ones, right? Mm-hmm. So I don't really know.
Observations also you see some amount of overlap, right?
Yeah, some amount, but not as big as this one, right? Because that's why when I do the averaging here, the thing don't go all the way down to 0. It stays a little bit up.
Okay. So no further questions, and let's thank Dario again. This talk is by Helena Popova. And we will be talking about the effects of meridional circulation on the dynamo wave in a one-dimensional model. Please.